Okay, the last part of 4.6 will be rational inequalities. And if you remember, recently we looked at rational functions. They look like this. You have polynomials in the numerator and the denominator. And so it's like a fraction. So what we're going to do is we're going to look at these rational expressions as inequalities now, so they could be greater than, less than or equal, and so on to 0. It's exactly the same as what we just did with polynomial inequalities. The only difference is with a rational expression, we've got two different things going on. We have the zeros for the numerator, or p of x. Those we're going to treat exactly the same as we did for the polynomials. Those are just zeros, so we're going to plot them. And we're going to plot them with solid dot, just like we did. And that's going to create some intervals on the line where we're going to find out if the function is positive or negative, or above or below the x-axis. Then we have the denominator. If you remember, the zeros of the denominator these are actually vertical asymptotes. And vertical asymptotes are the same thing. They're going to create more intervals on that number line. And since they're zeros, they're still very similar to this. The only difference is when you have a 0 for d of x, even though you're going to plot it on the line and it's going to create a interval break, you can never actually be at that point. So we're going to plot these with an open circle. And then the only other thing we need to do is the same as before. Pay attention to multiplicity, and that applies to all of these. So again, if we have an odd multiplicity for these zeros or for a vertical asymptote, then the graph is going to shift to the other side of the x-axis once you go past that point. Or if it's an even multiplicity, so you have like 2 zeros, or this, with vertical asymptotes you can't really have that, but that's where you're going to bounce, and the equation will stay on the same side of the x-axis if you have an even multiplicity. All right, so that's it. Really, the rules are pretty much the same except for this. So let's try one, and then we'll do one more. So let's look at this one. So we have x squared over 3x, x squared minus 2x minus 3, and this time we've got an inequality. So obviously, if we're looking for zeros, the first thing you do is you factor the numerator and the denominator. So we need to do that. So that's going to look like this. Take an x out of here. And then for the denominator, this will factor like this. So if you multiplied this out, you'd get back to this. So we're working with factors because now we're looking for zeros here and vertical asymptotes here. So step 1, factor. Step 2, plot the points, just like we did with the polynomials. solid dot for zeros, so the zeros are actually at x equals 0, and x equals minus 3. And then we also plot the vertical asymptotes, which are the zeros again of the denominator, and they're going to be 3 and minus 1. But we have to be careful here. We want to use an open dot, and we want to do that to remind us that even though this is an equal, greater than or equal, we can never actually equal minus 1. So if we want to use an interval that includes minus 1, it's always going to be one of those smooth brackets, because minus 1 and 3 are not in the domain. They're asymptotes. Okay. Then the next thing that we did before, now here's our intervals here that we're looking at. You don't have to draw these lines, but it just makes it more useful for me. So here's our intervals where the equation's going to move around. So 0 is a great test point. Unfortunately, it's taken. So pick something else that's easy, like 1. Okay, let's plug 1 in here and see if the function is positive, which means we're above the x-axis, or negative, which means we're below. And that would be in this interval, because that's where we're choosing our test point, which is 1. So if I plug 1 in here, I get 1 times 4, 3 plus 1, over 1 minus 3, that's minus 2, times 1 plus 1 is 2. I don't care again what the number is, the solution. I just want to know, is this positive or negative? Well, this is going to be a positive over a negative, but that turns out to be a negative. So in this range, we're below the x-axis, or less than 0. The multiplicities are 1 everywhere, so we're going to change every time we cross a boundary, even a vertical asymptote. So we're going to go from minus to plus here, plus to minus to plus here, plus to minus here, minus to plus here. Okay, last thing we need to do, I want all of the intervals where I'm greater than or equal to 0 or on or above the axis. So that would be here, because I'm positive, so I'm going to want this interval. I'm going to want this little guy here, and then this one out here. So again, I can use this because it's a 0. So we're going to start at minus infinity, go to minus 3, and we're going to include minus 3. Then we're going to pick up this guy, but I can't include this because it's an asymptote. So I want to start at minus 1 and go to 0. But again, 0 I can include. It's just a 0 of the numerator. And then finally, again, starting at 3, but I can't include it since it's not in the domain. And on to infinity, and that's it. Okay, one more example, because this example, I don't know how much experience we've had adding, subtracting, things like that, 2 of these. So here's another kind of problem you might get. Looks pretty simple, but there's actually a lot of work here. Okay, just like with the polynomials, you have to move everything to one side and have an inequality with 0. So it doesn't matter which way you do this. I could subtract this over here, I could subtract this over to this side. You're going to get the same answer either way. So what I'm going to do is I'll just subtract this over here. So x minus 3. Now if I subtract this whole thing from both sides, it'll look like this. So we're here. Okay. I need to subtract these rational equations so that I can get one equation, and then I need to factor all that. So this is just subtracting two fractions, and whenever you add or subtract fractions, the bottoms have to match. So that's going to make this easy. If I multiply this bottom times this one, and this bottom times this one, they'll both look the same. They'll look like x minus 6 times x plus 4. So let's do that here. So I got x minus 6. I'm going to multiply that by x plus 4. But whenever you multiply the top or bottom of a fraction by something, you got to multiply the other side by the same thing. So that means this x minus 3 here, I also have to multiply by x plus 4. Okay, and you can see if I cancel these, it's the same fraction, right? So we haven't changed it. We've just modified it so that we're going to be able to add it or subtract it in this case from this one. For this one, since the bottoms have to match, I'm going to multiply this by x minus 6. Well, multiply this by x minus 6, got to multiply the top by x minus 6. Now I can subtract them. So everything, the numerator's the numerator. So that's going to look like, I think I better move down here. We're going to need some space. So there's our common denominator. So if I subtract these, I just put everything over the common denominator. So I have this minus all of this. Okay, that's already factored, and in fact we can see that the asymptotes are going to be a 6 and minus 4. That's fine. The problem is the top. This is not factored. This is a couple factors, but it's minus a couple other things. So what I need to do here to factor this, I have to expand everything out, combine like terms, and then factor that result. That's how you have to do this. So if I multiply this one out, I got x squared plus 4x minus 3x, that's just plus x. And then minus 3 times 4, that's minus 12. Now be careful here. It's minus whatever this whole thing is here. So let's set it up like that so we don't miss a minus sign. Okay, now let's work on this. So again, minus all of that. So we're going to use the parentheses there. X squared plus x minus 6x, that's minus 5x minus 6. Now, when I remove the parentheses, we've got x squared plus x minus 12 minus x squared minus and a minus, that's plus 5x, minus, and a minus, that's plus 6. All of that over our denominator, which is already factored. Okay, so x squareds cancel. I add up the x's, that's going to be 5 and 1, that's 6x. Minus 12 plus 6, that's minus 6. So that's the top. And then finally, we can factor this. I can factor a 6 out. So here's our final factored rational expression. Again, get it to 0, and then do whatever you have to do to get a final form where the numerator and the denominator are factored. Now we're ready to go. Draw your line. Start with your zeros. Well, we only have one 0. That's at x equals 1. Okay, so that's going to set up a boundary. Okay, take a look at the bottom. Those are your asymptotes. I actually have two. I have one at 6, one at minus 4. So way out here at 6. And again, open circle on that one. And at minus 4, open circle. Again, they're asymptotes. They're not in the domain. We can't include them in our solution. Okay, now we're lucky. 0 is somewhere in this interval, so we can use that as our test case. So I got 6 times 0 minus 1 is minus 1. Down here I got 0 minus 6 and 0 plus 4. So what we have here is a negative over a negative. That's going to be a positive. So in this region, the rational expression is positive. That means it's above the x-axis. More important, it means it's greater than 0. So we're looking for other things. Again, all the multiplicities here are 1, so it's going to change every time we cross a boundary. So from here to here, we go plus to minus. From here, we go minus to plus. From here, we go plus to minus. Since I want to be less than 0, I'm looking for negatives. So I'm looking at this range here and this range right here. This one starts at negative infinity, goes to minus 4, and again, that's an open circle, so I don't include it. And I'm going to combine that with starting at 1, and now I almost put a square one there. Since it's strictly less than, we can't include it anyway, so I got to go like that. Then I go to 6, and 6, it wouldn't matter what that was, we can't include that anyways. There's your solution, and that's it for chapter 4.